motion of a falling object. So what is the purpose of this lab? This lab's purpose is to observe an object's motion moving with non-constant velocity and compare real-world versus computational scenarios. So some fundamental principles we need to know for this lab are kinematic motion and Newton's second law. So for kinematic motion, there's two major forces that act upon the system. We have gravity and then the drag force. So the drag force is equal to negative b times the speed squared times y hat, which is the unit vector in the y direction. Whereas Newton's second law is the acceleration of an object is dependent on the force and mass of the object. In this case, at a non-constant velocity, acceleration is not equal to zero, and therefore there is a net force acting on the object. So in the real world scenario, the net force is equal to the sum of the force of gravity and the force of drag on the object. So here's our experiment. So our system is the paper ball, whereas our surroundings are the atmosphere, which is the air, and then the earth. So during projectile motion, the velocity in the x direction is constant, but the velocity in the y direction is non-constant, as it is acted upon by a non-zero net force, which is the sum of gravity and air resistance. So here's my code. The ball's mass was estimated to be around 0.05 kilograms. And then the position vector started at the 0, point, which is the origin, whereas the velocity had initial velocity as it was thrown of 1.88 and then 2.11 in the y direction. So our y hat is a vector pointing solely in the y direction, so 0, 1, 0. And then our b was determined experimentally based on the observed data, which is 0.093. So this is the proportionality constant for the drag force. And then to calculate our net force for the model with drag, we would use this formula down here, which is the F gravity is equal to negative mg times y hat. And then the drag formula is the vector pointing in the y direction of the formula for drag, which is b times the velocity y squared in the y direction, of course. So for the model with only gravity, b would be set equal to 0, whereas for the model including drag, b would be set equal to the proportionality constant. So our results found that the computational curve with gravity only showed a much more pronounced curve, as there is no drag force, and as a result there is nothing to decrease the acceleration of the object due to gravity, whereas with the drag force there is less curvature, and as the drag force points in the opposite direction of gravity, resulting in a smaller net force acting on the object, which means a smaller acceleration. So as you can see in the graph, the orange line depicts the gravity only, whereas the green line, which is much more similar to experimental value, depicts the gravity plus the drag. So when comparing these two models, it can be seen that the acceleration in the gravity model is changing at a constant rate. It feels a constant net force. So this is based on Newton's second law, of course, whereas the model with drag has a non-constant acceleration as a result of the drag force. And according to Newton's second law, this object feels a non-constant net force. And as you can see, this is an inverse sigmoidal curve rather than a just straight linear curve. So what are some possible sources of error? Several errors could have accounted for the discrepancies between the observed and the predicted motion, as there's probably a more exact proportionality constant that could be determined experimentally than the one that we determined. There's also possible improper tracking or the camera angle and movement of the camera while recording the video. And then because the object was a crumbled up piece of paper, there's unequal mass distribution which could cause a more pronounced drag force. If the object was thrown straight up, it would take longer to reach the ground as it was thrown with the same initial velocity, the only difference between the trials being the angle at which it is thrown. So if it's thrown straight up, the angle is 90 degrees, which would be equal to the sine of 1. So when you plug this in to find how long it would take to hit the ground, you get for projectile motion, t is equal to 2 times v sine theta divided by g, whereas straight upwards is t equals 2v divided by g. So because of this, at any angle other than 90, the sine of theta expression is going to equal less than 1, which would cause the time to be shorter. So the best way to determine the terminal velocity of the object is to use the drag force model. And an object at terminal velocity will have a net force of 0, where the velocity versus time graph will be flat and the position versus time graph is a constant slope. So this can be seen on the two graphs towards the end after t equals 8. You can see that there is a constant velocity and there is a net force of 0.